August 19, 1942. Dieppe, France. Dawn breaks over the English Channel as 6,000 Allied troops storm the French coast. Their mission: capture a heavily defended port and prove the Allies can take Europe back from Nazi Germany. 9 hours later, the beach runs red with Canadian blood. 3,367 casualties. A 68% casualty rate. Bodies float in the surf while German machine guns rake the stones. Not a single objective achieved. The raid becomes the bloodiest disaster in Canadian military history, and it teaches Allied commanders one brutal lesson: you cannot capture a heavily defended port. But without ports, the planned invasion of Nazi-occupied France is impossible. Supply ships need deep water harbors. Tanks need concrete docks. Armies need millions of tons of equipment offloaded every week. The French coast stretches 3,000 miles, and the Germans defend every single port with concrete bunkers, artillery batteries, and elite troops. Allied planners stare at maps in London, searching for answers. Every simulation reaches the same conclusion: without ports, an invasion fails within days. The Wehrmacht will push the Allies back into the sea, just like they did at Dunkirk. D-Day will become history's largest graveyard. What the generals don't know is that in a cramped office at the Railway Research Service in Derby, a 30-year-old engineer with no naval experience is sketching something that naval architects will call impossible. He's designing a harbor that can cross the English Channel. Major Alan Beckett doesn't look like someone who will change history. No prestigious degree from Cambridge. No connections to the Admiralty. He's a civil engineer who spent his pre-war career building railway bridges in London. But in his notebook, he's solving the unsolvable: how to land an entire army on an open beach with no port for 500 miles. The concept defies every rule of naval engineering. Floating roadways that flex with 20-foot tides. Concrete caissons the size of 5-story buildings. Artificial breakwaters protecting a square mile of ocean. Military planners will dismiss it as fantasy. Senior engineers will declare it structurally impossible. The Royal Navy will call it a waste of concrete and time. But Major Beckett keeps drawing. Because he understands something the experts don't. If the Allies cannot bring a port to France, Hitler has already won. The clock is ticking. The invasion must happen in 1944, or never at all. The problem haunts every Allied war room. Winston Churchill obsesses over it. General Dwight Eisenhower loses sleep calculating tonnage requirements. By late 1942, everyone agrees, an invasion needs 12,000 tons of supplies landing every single day. Without it, troops run out of ammunition, fuel, food. The invasion stalls. Germany counterattacks. The war drags on for years, maybe decades. Churchill remembers the problem from the First World War. In 1917, as a young lord of the Admiralty, he sketched designs for temporary harbors during the Gallipoli campaign. The idea went nowhere. 25 years later, the same engineering challenge remains unsolved. After Dieppe, the situation becomes desperate. Allied intelligence confirms that Hitler has issued Führer Directive 4040, fortify every port in France. The Germans pour concrete by the thousands of tons. Cherbourg, Calais, Le Havre, every harbor transforms into a fortress. Attempting to capture any of them will cost tens of thousands of lives, and probably fail. The British War Office establishes a committee to study the harbor problem. They bring in the nation's top civil engineers, led by Bruce White, a veteran engineer overseeing military construction. The committee reviews dozens of proposals. Every solution hits the same obstacles: weight, wave action, tidal range. The Normandy coast experiences 18-foot tides. The English Channel produces waves that have destroyed natural harbors for centuries. Building something artificial seems like madness. Naval architects present calculations showing that any artificial structure will collapse in the first storm. Ship designers point out that towing concrete across 100 miles of open ocean violates basic maritime physics. Military logistics officers argue there isn't enough construction capacity in all of Britain to build such a project. Time estimates stretch to 5 years, far too late for any invasion in 1944. One engineer proposes floating steel pontoons. Testing shows they buckle in 8-foot waves. Another suggests anchoring ships in a line as a breakwater. The Admiralty refuses to sacrifice hundreds of vessels. A third design calls for underwater barriers, but the sandy bottom provides no stable foundation. Every solution fails in scale models or requires resources that don't exist. The expert consensus hardens: artificial harbors cannot work. The invasion will need to capture a port immediately, accept massive casualties, or wait indefinitely for some technological breakthrough that may never come. Senior commanders begin considering alternative strategies: longer campaigns, different invasion sites, negotiated settlements. The stakes couldn't be higher. By autumn 1942, the Soviet Union teeters on collapse, bleeding out at Stalingrad. Stalin demands a second front to relieve pressure on the Eastern Front. American political will requires action before the 1944 presidential election. Britain's economy cannot sustain years more of total war. The window for invasion is closing. On May 30, 1942, Churchill's frustration boils over. He sends a terse memorandum to the Chief of Combined Operations. Piers for use on beaches. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves. The memo lands on Bruce White's desk. He convenes his committee of Britain's finest engineering minds. They need revolutionary thinking, someone willing to ignore conventional wisdom. White begins recruiting civilian engineers from private firms, expanding his team to over 150 specialists. Among them is Major Alan Beckett of the Royal Engineers. He's been working on military bridging problems at the Railway Research Service, a backwater posting for an officer with no combat experience. His specialty is railway bridges, how to make structures that handle tremendous weight while flexing with temperature changes and ground movement. Beckett receives the assignment on a Tuesday morning in June. Build a harbor that can cross the English Channel. Make it operational within 12 days of the invasion. Design it to handle 5,000 tons per day. Have preliminary plans ready in 3 weeks. It's impossible. Which means it's his kind of problem. Alan Harry Beckett was born on March 4, 1914, in East Ham, London, about as far from the sea as you can get in England. His father worked in manufacturing. Young Alan showed talent for mathematics and engineering, earning admission to London University to study civil engineering. Not Oxford. Not Cambridge. Just a solid technical education for a middle-class kid who likes solving problems. He graduated in 1936 and joined a London engineering firm, designing bridges and railway infrastructure. Steady work. Forgettable projects. When war broke out in September 1939, Beckett was 25 years old with no military background. He could have claimed exemption as an essential civilian. Instead, he volunteered for the Royal Engineers in January 1940. The Army assigned him to bridging duties. Not glamorous. While pilots fought the Battle of Britain and commandos raided occupied Europe, Beckett calculated load tolerances and taught soldiers how to assemble Bailey bridges. By 1942, he's posted to the Railway Research Service in Derby, working on experimental bridge designs. His commanding officers note his talent for unconventional solutions, but question his lack of practical naval experience. The harbor problem arrives on his desk as a theoretical exercise. White's committee needs ideas, even crazy ones. Beckett starts where he always starts, with the fundamentals. What makes a bridge work? It has to support weight. It has to flex. It has to anchor securely but allow movement. He studies the Normandy coastline. 18-foot tides. Sandy bottom. Exposure to Atlantic storms. Any rigid structure will snap. But what if the structure moves with the tide instead of fighting it? Beckett begins sketching in his notebook. He envisions roadways that float on pontoons, rising and falling with the water. The roadways connect to pierheads mounted on telescoping legs, spuds, that can extend down to the seafloor but slide up and down as the tide changes. The roadways themselves need to flex in all directions, up and down with tides, side to side with waves, even twisting with currents. He calls his design Whale, the floating roadways that breach like ocean mammals, diving and surfacing with the tide. The challenge is the math. Railway bridges move inches. These roadways need to move 20 feet vertically and maintain their structural integrity. Traditional rigid materials won't work. Beckett designs a system of steel spans connected by flexible joints, like a massive mechanical spine. Each section measures 60 feet long and weighs 10 tons, but the joints allow independent movement in multiple axes. For the pontoons, he specifies hollow steel drums filled with air, beetles, that provide buoyancy. The key insight is distributing the weight, not one massive platform but dozens of connected segments, each adapting to local wave and tide conditions independently. After 3 weeks of 18-hour days, Beckett submits his proposal. His design covers 40 pages of calculations, blueprints, and materials lists. He's never built anything remotely like it. He's never worked in maritime engineering. His credentials are thin, but the mathematics are sound. The concept is revolutionary, and critically, it can be built with existing British industrial capacity. Bruce White reads the proposal twice. Then he calls a meeting. Every senior engineer in the Mulberry Committee needs to see this. The room is about to erupt. ACT-4 Secret Workshop, 500 words. October 1942. A cove near Conwy, Wales. Hugh Iris Hughes, a Welsh civil engineer, supervises workers pouring concrete into enormous molds. He's building prototypes of floating concrete caissons, massive hollow chambers codenamed Phoenix. Each one measures over 60 feet long, 40 feet wide, and weighs 6,000 tons. Simultaneously, at a workshop in Derby, Beckett oversees construction of a whale prototype. Engineers weld steel spans with flexible joints, testing how much movement the connections can handle. The first test section bends 12 degrees in both directions before the joints bind. Beckett orders the tolerances increased. The work happens in absolute secrecy. Workers sign the Official Secrets Act. They know they're building something for the invasion, but not what. The code names sound absurd: Whale, Beetle, Phoenix, Bombardin. Churchill personally approves the cryptic names. If German intelligence intercepts reports about whales and beetles, they'll dismiss it as noise. The first full-scale whale section is ready for testing by November. Engineers assemble 3 60-foot sections end-to-end and tow them to a Scottish lock for sea trials. The structure needs to survive 8-foot waves and handle loads of 50 tons, trucks, tanks, and jeeps driving on roadways in open ocean. The test almost kills everyone. The initial anchor design rips free in 5-foot waves. The roadway twists 90 degrees and nearly capsizes. Engineers scramble to attach emergency lines before the whole thing sinks. They tow the mangled prototype back to shore. That is never going to work, a Royal Navy observer writes in his report. The structure lacks the rigidity to function as a load-bearing platform in operational conditions. Recommend termination of the whale project. Beckett studies the wreckage. The concept is sound, the execution needs refinement. He redesigns the anchoring system, adding multiple connection points to distribute stress. The flexible joints need dampeners to prevent oscillation from building into destructive resonance. It's basic engineering, like shock absorbers on a car, but applying it to a 60-ton floating roadway is unprecedented. Meanwhile, Hughes's Phoenix caissons face their own crisis. The first full-scale caisson sinks during launch. The massive concrete structure is supposed to float, but water floods the internal chambers faster than pumps can evacuate it. Engineers realize the concrete is cracking under its own weight before it even touches water. The committee meets in emergency session. Costs are spiraling. The whale doesn't work. Phoenix caissons keep sinking. Senior engineers recommend canceling the entire project. We are pouring resources into a fantasy, one admiral argues. Let's focus on capturing Cherbourg quickly. Bruce White faces the bureaucratic death of the project. But Churchill's main memo still stands: don't argue the matter. Find the solution. White gives Beckett and Hughes 3 months. Fix the problems or the project dies. In total, Britain has committed to building over 600 Phoenix Caissons, 10 miles of whale roadways, and enough support structures to create 2 harbors: Mulberry A for the Americans at Omaha Beach, Mulberry B for the British at Gold Beach. The target date for completion, April 1944. 4 months before the invasion, nobody can officially confirm exists. The clock is running. January 18, 1943. A conference room at the War Office, London. 60 engineers, military officers, and logistics specialists crowd around tables covered with blueprints. Cigarette smoke hangs thick in the air. Bruce White calls the meeting to order. Major Alan Beckett stands to present. He's 38 years old, rail-thin, exhausted from 3 months of round-the-clock testing. He places his revised whale designs on the display board. "Gentlemen, the fundamental problem is treating the structure as a bridge," Beckett begins. "Bridges resist movement. These roadways must embrace it." A Royal Navy captain interrupts immediately. "Major, I've reviewed your stress calculations. You're proposing flexible joints that allow 18-foot vertical displacement. The flex points will fatigue and fail within days. It's structurally unsound." "In a rigid structure, yes," Beckett responds. "But the joints distribute stress across multiple connection points. Like a human spine. Individual vertebrae move minimally. The cumulative effect allows significant flex." A civilian engineer from a major construction firm stands. "Even if the roadways work, which I doubt, you cannot anchor them in sand. The bottom off Normandy provides no purchase. First storm, the whole structure drifts to Belgium." Beckett remains calm. "We've solved the anchoring problem. The pierheads use telescoping spuds, steel legs that penetrate 20 feet into the sea floor. The legs slide within fixed sleeves, allowing vertical movement while maintaining position. During testing, we've achieved stability in 12-foot swells." The room erupts. 6 conversations start simultaneously. Some engineers examine the blueprints more closely. Others shake their heads in disbelief. The naval officers argue that the spud concept violates maritime engineering principles. Load-bearing structures require fixed foundations. Allowing the foundation to move is madness. An admiral pounds the table. "Gentlemen!" The room quiets. "Major Beckett, your proposal requires us to commit nearly all of Britain's construction capacity for 18 months. If this fails, we have wasted resources we cannot recover. We need certainty, not innovation." "With respect, sir," Beckett says quietly, "certainty got 3,000 men killed at Dieppe. If we follow conventional engineering, we don't invade in 1944. Probably never invade at all." The silence stretches. A voice from the back breaks it. "Let him continue." Everyone turns. It's Hughes, the Welsh engineer. "The Phoenix Caissons work. We've solved the cracking problem by reinforcing the internal structure with a steel framework. They float. They're stable. But without functional roadways, they're just expensive bathtubs." White stands. "We've been authorized to proceed by the Prime Minister himself. The question isn't whether to build Mulberry. The question is which design gives us the best chance of success." He looks around the room. "Every engineer here has legitimate concerns. But I've watched Major Beckett test and refine this design for 4 months. It works. In a Scottish lock," someone mutters. "The English Channel is not a Scottish lock." "True," White acknowledges. "Which is why we're conducting full-scale trials at Garleyston starting next month. We'll assemble a complete harbor section in conditions that simulate the Normandy environment. If it fails, we go back to the drawing board." The room erupts again. Arguments intensify. Some engineers support Beckett's innovative approach. Others demand more conventional solutions. The logistics officers point out that even if the harbor works, construction requires 200,000 workers, tens of thousands of tons of steel and concrete, and coordination across 200 civilian firms. It's the largest engineering project in British history. Finally, White makes the call. "We're proceeding with Whale. Full-scale construction begins in March. Major Beckett, you'll oversee final design refinement and coordinate with the manufacturing teams. Gentlemen, Churchill has personally guaranteed this project receives priority over everything except Spitfire production. Anyone who cannot commit fully should leave now. Nobody leaves. For all their doubts, every person in the room understands the stakes. As the meeting breaks, a senior admiral approaches Beckett. Major, I hope you're right. Because if those roadways fail on D-Day, you'll have killed the invasion before it starts. Beckett nods. Sir, if the roadways fail, we'll have much bigger problems than my reputation. If this story amazes you, wait until you see what happens on D-Day. Consider subscribing so you never miss these incredible untold stories from history. If this story amazes you, wait until you see what happens on D-Day. Consider subscribing so you never miss these incredible untold stories from history. March 1943 through June 1944. The British Isles transform into a factory. From Portsmouth to Liverpool, 200 construction firms pour concrete, weld steel, and assemble components for the two Mulberry Harbors. The statistics defy imagination. Engineers build 147 Phoenix caissons ranging from 200 to 204 feet long, weighing between 1,500 and 6,000 tons each. The largest stand 6 stories tall. They require 600,000 tons of reinforced concrete, enough to build a city. For the whale roadways, manufacturers produce 6 miles of flexible steel spans, each section weighing 10 tons. The Beetle pontoons, hollow steel cylinders providing buoyancy, number in the thousands. 23 pier heads, each mounted on 4 telescoping spuds, undergo precision engineering to ensure the hydraulic mechanisms can handle constant operation under combat conditions. Over 45,000 workers labor around the clock. Most have no idea what they're building. Foremen distribute components across dozens of sites. A factory in Bristol makes flexible joints. Shipyards in Glasgow cast caissons. Engineering works in Derby fabricates spud mechanisms. Only White's Core Committee understands how the pieces connect. Beckett spends 18 months traveling between construction sites, troubleshooting problems. The flexible joints keep cracking until metallurgists develop a new steel alloy. The Beetle pontoons leak until welders modify their techniques. The spud mechanisms jam until engineers add lubrication systems. Each problem costs weeks and threatens the timeline. By April 1944, the components are ready. The massive Phoenix caissons dot the British coastline like beach whales. Workers paint them with protective coatings and fit them with flood valves. When the invasion begins, ocean-going tugs will tow them across the channel at 4 miles per hour, the largest naval convoy in history. The British conduct final operational tests in absolute secrecy. A complete harbor section assembles in the Firth of Clyde. Engineers drive tanks across the whale roadways. The structure flexes and groans but holds. They simulate 8-foot waves using tugboats. The roadways twist and bend, joints flexing up to 20 degrees. But they don't break. It actually works. White writes in his diary on May 15, 1944. God help us, Beckett's mad design actually works. June 6, 1944. D-Day. 156,000 Allied troops storm 5 beaches in Normandy. By nightfall, they've secured tenuous footholds. But the landing is just the beginning. The real test starts now. Can they sustain the invasion? Within 24 hours, the first Phoenix caissons depart British ports. Tugboats strain against the massive concrete structures, pulling them across the channel at barely walking pace. German U-boats hunt them, but the sheer number of Allied ships provides protection. The caissons look like office buildings crawling across the ocean. By June 9th, D-Day +3, the first Phoenix caissons arrive off Gold Beach. Royal Navy personnel trigger the flood valves. Millions of gallons of seawater pour into the hollow chambers. The massive structures sink in controlled descents, settling into position on the sandy bottom. Engineers link them end to end, creating a breakwater half a mile long. The whale roadways arrive next. Crews maneuver the floating sections into position, connecting them to the sunken caissons. The spud pierheads deploy their telescoping legs, anchoring firmly 20 feet down. Within days, a complete artificial harbor, codenamed Port Winston by the British, takes shape off Arromanches. The American Mulberry A at Omaha Beach develops similarly, though construction proceeds slower due to rougher seas and ongoing German artillery fire. By June 18, 1944, D-Day +12, exactly as planned, both harbors are operational. Ships pull alongside the pier heads. Trucks drive across the whale roadways, wheels humming on steel. The roadways rise and fall with the 18-foot tide, flexing and twisting with each wave, but holding firm. Then the storm hits. June 19th through 22nd. A massive northeastern gale, worse than any storm in June for 40 years, slams into the Normandy coast. Waves reach 20 feet. Winds scream at 40 miles per hour. The Allied supply operation grinds to a halt as hundreds of landing craft are driven ashore and smashed. The American Mulberry A, more exposed to the storm's fury, disintegrates. Phoenix caissons crack and shift. Whale roadways rip free from their anchors. Within 3 days, the harbor is destroyed, $1 billion investment reduced to twisted steel and broken concrete. At Gold Beach, Mulberry B fights for survival. The waves exceed design specifications. Beckett's flexible roadways twist through arcs approaching their maximum tolerances. Several beetle pontoons rupture and sink. But the spud mechanisms hold. The joints flex but don't break. The fundamental engineering, embrace movement, don't fight it, saves the structure. When the storm finally passes, surveyors assess the damage. Mulberry A is unsalvageable. But Mulberry B, though battered, remains functional. British engineers make repairs within 48 hours. Ships resume docking. The harbor operates for 10 months. Through Mulberry B, the Allies land 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. The tonnage exceeds the capacity of the port of Dover, one of Britain's largest harbors. Without it, the invasion stalls. With it, the Allied advance becomes unstoppable. German commanders are stunned. They base their defensive strategy on controlling ports. General Erwin Rommel wrote in March 1944, "The enemy will not be able to land without harbor facilities. We have fortified every port. The invasion will fail on the beaches." But the Allies brought their own harbors. After the war, Luftwaffe Field Marshal Hugo Sperl testified, "We believed you would need to capture Cherbourg immediately. When our reconnaissance planes spotted artificial harbors, we thought it was a deception. By the time we understood what we were seeing, it was too late." An American colonel, witnessing Mulberry B in operation, wrote to his wife, "We are watching trucks drive across roads floating on the ocean. If I hadn't seen it myself, I would never believe it possible." General Eisenhower later wrote, "The artificial harbors proved of great value and made possible the rapid buildup of our forces. Without them, the invasion would have been impossible." Alan Beckett never sought recognition. After the war, he returned to civilian engineering, joining the firm of Sir Bruce White, Wolfe Barry and Partners. He worked on international projects, bridges in Africa, harbor facilities in Asia, establishing a quiet reputation as a brilliant structural engineer. He rarely spoke about Mulberry. When asked about his wartime service, he deflected. "Many people contributed," he would say. "I solved one small problem among thousands." But his contribution was hardly small. The flexible joint technology he developed for whale roadways influenced post-war offshore engineering. Modern floating bridges use similar principles. Oil rig platforms employ spud leg designs directly descended from Beckett's pier heads. The concept of structures that move with environmental forces rather than resisting them became fundamental to marine engineering. The Institution of Civil Engineers recognized his achievement decades later. In 1984, they awarded him the George Stephenson Medal for Engineering Innovation. At the ceremony, then 80 years old, Beckett gave a brief speech. "Good engineering solves problems without pride. The harbor worked because many brilliant people contributed pieces. I merely drew the picture." He was wrong. Beckett provided the crucial insight: embrace movement. That single concept transformed an impossible challenge into an engineering triumph. Beckett died on June 19, 2005, 61 years to the day after the Great Storm tested his creation. He was 91 years old. His obituary in the Times ran 8 paragraphs. Most people who read it had never heard of Mulberry Harbors. But veterans remembered. At his memorial service, a 92-year-old veteran of the Royal Engineers read a letter. "Major Beckett, you gave us roads across the sea. Because of what you built, we had ammunition when we needed it, fuel for our tanks, food to eat. Because of you, we came home. Thank you will never be enough." Today, remnants of Phoenix caissons still stand off Arromanches, massive concrete monoliths visible at low tide. The French government protects them as historic monuments. Tourists photograph the strange structures jetting from the surf, often not understanding what they're seeing. They're looking at the reason the Allies won World War II. Because when everyone said artificial harbors were impossible, a 30-year-old railway engineer proved them wrong. He designed roadways that flexed. He created harbors that crossed oceans. He turned impossible into inevitable. The experts called it illegal engineering. Churchill called it essential. History calls it genius. And Major Allen Beckett, the humble engineer who never wanted fame, called it Tuesday. Just another problem to solve. Just another bridge to build. Except this bridge stretched across the English Channel, carried an entire army, and changed the course of human history. The technology his team developed saved hundreds of thousands of lives and shortened the war by months, maybe years. Modern offshore engineering, platforms producing 40% of the world's oil, floating wind farms, emergency disaster relief bridges, all trace their lineage to a Welsh cove and a Scottish loch where engineers first proved that harbors could float. Sometimes the greatest heroes are the ones who solve problems nobody else thought solvable. Sometimes saving the world looks like welding steel joints in a workshop in Derby. Sometimes victory is built by people nobody remembers. Until now.